Now here's a related question. How many possible committees of 3 people can be chosen from the 5 people? We could list the possibilities. If the people are A, B, C, D, E, then we could list possible committees of 3. Systematically, we could list A, B, C, A, B, D, A, B, E, B, C, D, B, C, E, B, D, E, I wasn't very systematic in that. I left out some that start with A. I left out A, C, D, A, C, E, and A, D, E. If we list these alphabetically, and you know better than I apparently do at the moment why we do it that way. But we have B, C, D, B, C, E, B, D, E, and then C, D, E, and that should be 10. Let's count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's correct. Now, how do I know that that should have been 10, and how did I suddenly discover I made a mistake there? Well, the mistake was fairly obvious. But I can reason out how many committees. First of all, let's make sure we understand that these are all the committees. Now, I could have listed CBA, but just like the Pentagon with the triangles, the order of these things doesn't matter if this is a committee. We're not choosing the officers of a committee. We're not putting people in order for a picture. We're just lumping 3 people together, maybe telling them go into this room and solve this problem. The order in which they're chosen makes no difference. So that what we've done is we've chosen what's called a combination as opposed to permutation of 3 people chosen from 5. Same idea as the permutation, except in the case of a combination, order is irrelevant. It doesn't matter. That's the meaning of the idea of a combination. Okay, let's see how we would calculate the number of combinations. Now, if we chose the people in order, it would look a lot like the permutation. We have positions 1, 2, and 3. 5 choices for the first, 4 for the second, 3 for the third. There 5 times 4 times 3 equals P of 5, 3. Ways to choose in order. But we said that order doesn't matter, that this is a combination. The order of the people chosen for the committee doesn't matter. So I'll make a note here, and then we'll look at on another page at how this works. But there are 3 times 2 times 1 orders in which 3 can be chosen. Now we're getting kind of cramped down here at the bottom of the page, so we'd better move on to a fresh sheet and expand this idea a little bit. For example, if we choose, if A, B, C is our choice, the permutations would allow A, B, C to have been chosen, or the orders in which A, B, and C could be chosen might be A, B, C, A, C, B, B, A, C, B, C, A, C, A, B, or C, B, A, listing those orders alphabetically. So these are the orders in which A, B, C could be chosen. And then our next combination was A, B, D. Well, there are 6 orders here. We could list them. There are 6 possible orders, right? And off on another page there, but you see what we mean. Okay, for every combination, there are 6 possible orders in which the combination could have been chosen. Now we could see that there are 6 possible ways, because if we're going to choose these 3 in order, there are 3 choices for the first, 2 for the second, 1 for the third, which is 3 times 2 times 1. There are 6, which is 3 factorial orders in which any combination could be chosen. So to get the number of possible combinations, we're going to say that the number of combinations C of 5, 3 can be calculated by taking the number of permutations, the number of ways the 3 could be chosen in order, divided by the number of ways of ordering the 3. So this represents a number of ways they could be chosen if they were chosen in order, but since order doesn't matter, we're going to divide by the 6 ways each could be ordered, or 3 factorial ways each could be ordered, and that's going to be our formula for the combinations. And we can generalize this to the combination of R things chosen out of N, where order doesn't matter. That's going to be the same as the number of permutations, the number of ways to choose them in order, divided by the number of ways to order the R objects, which is, of course, just R factorial. So there's our formula for the combinations, and we see how it comes from the formula for permutations. If we put these together, the number of permutations is going to be N factorial divided by R factorial, by N minus R factorial. But then we divide that by R factorial, which gives us another R factorial in the denominator. And there's a formula for the number of combinations.